one of the there was two pulsar capital that time. So actually three, Max Planck Bonn, Jodrell Bank Center for Astrophysics and RRI. And there are lots of very revolutionary pulsar work at RRI. Deep Anjanda is from that time. So after doing his PhD, he moved to Europe and did his postdoc at Max Planck, and then he is at NCRA, and he is one of some of the last Mohicans who understands the pulsar emission mechanism and interior structure. So it is to you, Deepanjan. So probably collar mic.
Hello. Can you hear me? Yeah. Okay. Hello. Hello. Yeah. Okay. So, okay. Good morning and welcome to a Friday where I must say that it has been a very lovely experience to be in IMSC, thanks to Professor Ghosh and colleagues and the organizers for asking me to join this occasion to be able to speak about neutron stars to you. And of course, Professor Bakshi, Manjuri is an old colleague. She has this habit of putting you very up, which I'm certainly not. So, but nonetheless, let us take us through this journey, and Professor Ghosh asked me to give a talk, particularly trying to give a flavor of neutron star and how neutron star is used for studying quantum mechanics and a few other areas of physics. So let me just to put you in perspective about the way astrophysics connects to the physics world. Is this my view, that in astrophysics what we do is that often there is a serendipitous discovery. You look at very special telescopes, look in the universe, you get a very interesting object, and then you start a field of physics by itself. And one such example is of course the cosmic microwave background. You detected it was serendipitous and you started a whole range of activity. But there is also another side of this, that as a theoretical physicist, you sit in a room, you scribble, you suddenly get a very, very exotic idea, and then you appeal. You go back to astrophysics, trying to figure out whether my idea is valid, and then when it is valid, you feel a feeling of triumph enters. And neutron star sort of falls in this both categories, as we'll see. And I have chosen this topic, which is called the extreme physics. Now, extreme, of course, is also a very subjective word. For example, I'm extremely happy to join you for the celebration of quantum mechanics. I'm extremely happy with the food, the colleagues. And so when it comes to physics, there are also certain things that you can define as extremes. And I tried to make a list. Sorry. Yeah. So I try to make a list of various extremes, and you can ask questions like, what is the extreme photon energy? Now you see there is these objects, gamma ray burst here, they have 1 peta-electron volt. Cosmic ray energy 10 to the power 20, even now slightly larger, 10 to the power 21, 22. And all these blue ones that you see here, the large list, they correspond to extreme like temperature, magnetic field, mass density. Now they are all associated with either neutron stars or magnetos. Okay. So just to just to give an idea, I picked up a few things. So you see that this object, come up with a question: what's the maximum mass? What is the most highest density? What is the highest magnetic field? And you end up having a large pool of quantities that fall in the neutron star category. Okay, so this is what we are talking about a neutron star and object. Yeah. More? Yeah, that's correct. And also, but it's not a very sustained. Yeah. So if you tell me something, I'll tell another extreme. Okay. Yeah, you're correct. Of course, we have, in fact, also electric fields, for example, you can go much higher in the laboratory.
Also doing heavy ion collision.
Yeah, you're absolutely correct, and that is what we want. I mean, from the just to see that these things can be. But I think the major problem, as you might realize, is the stability as well. Okay, so he is correct that there are many advances in laboratory physics as well. But this is what one would like to say. Okay, so now out of that neutron star, these extreme physics laboratories. The quantum matter is something which is very much connected to these compact objects like white dwarf, neutron stars, cosmic rays, okay? And of course, there are other areas of astrophysics which connect to things like strong gravity, early universe, and things like that. So this is just my hierarchy. I try to make something like this, and so we will today mostly focus on this top part, okay? Now let's, I was hoping that, Professor Ghosh said that there would be a lot of MSc students and so on. I don't see many, but I guess we could, essentially share our. I'm at that level, please. Okay. I'm very happy to okay, yeah, well, I will probably, not go very. Okay, so to begin this story of neutron star astrophysics, and this is what I was taught when I was actually joined as a student in Raman Research Institute, is that you took an experiment, thought experiment, that let's take Earth and start putting mass on Earth, okay. So this very simple thought experiment actually, so this is your mass axis, and this is your radius axis, and this curve, this is where Earth is, and you put on getting mass. So your radius goes as to the power 1/3 because it's like density going up, okay. Now you might know already that when you are here right at this top, it is Jupiter. Now in Jupiter the thing suddenly flattens and goes on the other way around. Okay, and the reason for this is because here, of course, you are putting on mass. The reason why we are, of course, standing here is because there is this electron shielding pressure. And as you go higher and higher, the localized electrons in the thing, they become much more delocalized. So you produce a sea of electrons, that is your degenerate quantities become more prominent, and then you start now dominating the degenerate pressure after that. And the fact is that you actually, if you go on adding that mass, now radius no longer goes as m to the power 1/3, but it goes the other way around. Okay, and this is the relation. So you put more mass, the radius keeps going down.
Earth is fixed, na?
Yeah, but I am doing a thought experiment.
Oh, okay.
I have a thought experiment where I am putting mass and asking the question that what will happen to this system, and this is what will happen. Of course, in reality, you don't put mass and make Jupiter. That's of course not true. But if you did that, and there is no internal source of energy, of course, okay, then this is what is going to happen. Now, this is not very far from the idea that Chandrasekhar get, because once you get your whole material doing your degenerate gas and come at the level of relativistic particles, that is C, you can't go anywhere, everything is filled up, the sea of electrons, then you actually collapse to this red line is your Chandrasekhar limit. Okay. And if you have electrons, this quantity would be half, you will get 1.4 solar mass. Okay. So this is the main idea of Chandrasekhar. when you have reached that limit, the theoretical idea is the star has completely collapsed, so it has no radius. But just before that limit, you could have a radius, and this also scales very well with the idea that it has 10 to the power 4 kilometers as its radius, which is typically. It's a remarkable formula.
Because h bar is appearing explicitly.
Yeah.
Except you're describing things that are thousands of kilometers in radius
Absolutely.
and millions of kilograms,
Yeah.
tens of millions of
I mean, it's
kilograms.
a triumph. Again,
It's an
it's a
extraordinary formula because it involves h bar.
Yeah. And it is really a triumph in that sense, if somebody really appreciates this. And not only that, you see, so subsequently, of course, this led to a Nobel Prize, and all of you know the work of Chandrasekhar. And like he was saying, of course, these things doesn't happen like putting mass. It happens by a stellar evolution, etc. But once the source, inside source goes away, you can basically approximate everything to this formula. And what happens is the star collapses, and when it collapses, the outer material of the star, it goes up like a nebula, sometimes a helium flash, and in the center, what you're left with is a white dwarf. Okay, so this is the idea of your how a compact object like white dwarf is formed. Yeah. Yes, please. Jupiter. Yeah. Well, it's not a coincidence, but if you simply write the binding energy total of the electron, that means Coulomb energy and the energy of the Bohr atom, okay, and you do a what is that called variational principle, the mass comes out to Jupiter. Coincidence? I don't know. Must be a coincidence.
Z is the number of electrons in each atom.
Yeah.
What
So half, this is for the electron, this quantity will become half, Z by A.
sorry, for
Atomic number and atomic,
half A. Okay.
okay? Yeah.
You're putting in more mass and the star is getting, the planet or whatever is getting more compressed, then why is Jupiter a gas planet?
Well, it has nothing, it is saying nothing
Not-
about
not
the,
to do with this,
it is saying
okay.
nothing about the state of the planet. It is saying that if you have mass and that the density can still be, simply calculated by r to the power 1 by 3. So if you go on increasing, obviously at some point it will become a rarer thing, right? You're not changing the state of matter,
Okay, I see.
right? Now what happens is now when you put a little extra mass on Jupiter, then suddenly it realizes that now I have more space to go down.
Okay.
Okay, because the way I understand it is that your electrons initially in the atom, they will look at 1s2, 1s, 2s, 3p, all these kind of things. But when you bring it closer, the wave functions overlap, and now you have a C. So you have more space. You transition to that.
I see.
Okay. It is some kind of phase. I mean, people don't call it a phase transition, but it is something. There are two pressures. One is this electron shielding pressure. The other one is this degenerate pressure.
So if you continue that line all the way to the red dashed,
Yeah. It
then
is
you derive the MCH.
MCH, and their radius is 0. Because I don't have any, that's my limit, the theoretical limit.
Ah.
Okay.
So you know something else happens when you reach
Yeah,
R
something else, and that is where we will, that's the topic of today's talk. So what happens when you, so that's the place where gravity has won, degenerate pressure has, done its job, and now something else will happen. Okay? Yeah.
not the continuation of this formula, right? I mean, here R will never be equal to 0.
No, this is before this. Here R will be in 0.
No, but I mean like you
No,
cannot
this
continue.
is not the continuation of that. This is only the continuation from here, where the gas is still non-relativistic. So you have a polytropic equation of state, which is 5 by 3, if you remember, and this is 4 by 3. I'm not going into those details, but just to give you a flavor of how this whole business is thought about. Okay, fine. So let's move on. Okay. So the next thing. Okay. So now what we do is we keep on putting mass. Okay. Now what will happen? I mean, we all know in experiment these days what happens, but this is what roughly will be the chain, and let's see. So when you go on putting more mass, at some point the chemical potential of the nucleus, it will be larger than your this rest mass energy. Okay. So at that time the nucleus tends to kind of come out and then you know that in an environment when you have an isolated neutron, it decays into proton, electron, and then antineutrino with a release of so much amount of energy, right? You go on further putting masses, you have more such neutrons, and then you also then get into this equation, which is a proton electron with a neutron, and so this is called the infamous inverse beta decay, right? And you can imagine a situation that I keep on putting mass, and at some point these two equilibrate, mu n is equal to mu p plus mu e, okay? And again I take a relativistic limit, Pc, P type momentum times C, okay, energy. Then you suddenly see that this all this equation actually neatly falls in this category, Np, that is the proton electron to neutron ratio of the A, basically becomes 1:1:8. A lot of protons have got into neutron capture, so you have produced a lot of neutrons. And when you have done all that thing in an equilibrium system, so now if I went on putting mass, okay, and only allowed this equation to happen, then you would produce a star which has 8 times more neutron than electron and proton. Fine? Okay. But more things happen when you go on increasing. For example, the next level of density can do the following, that you have an chemical potential which is greater than the muon, which is another lepton, mc square, which has a different energy, rest mass energy. And then when this happens, your neutron now can basically do this p plus pu. This is this formula, but now for the muons, and then the proton and muon can do. And then instead of neutron, you can apply the same idea, that you have not this electron, but now you have a lot of muons. Yeah, sorry, neutrino people, yeah, definitely, yeah, sorry, yeah. Given that, this is what is going to happen. Oh, I think I did the plus, but somehow got it. Okay. So now, so this thing continues. I mean, we don't have to do very fancy things. And people, of course, talk about a lot of fancy things in neutron star. But the basic idea is this: go on pushing, look for the next lepton, and then you use your equation, and then you will end up getting some kind of a particle. Except that when you go to higher and higher densities, you know I can create this hyperons and so on, but then I don't know what to create. Okay, there are a lot of other uncertainties that comes in, and I also myself don't know how people work on this. That goes into QCD and so on, those kind of here. But this is the basic idea of a neutron star. See, if you do this thing PC, and PC, that means first of all, why? Let me tell you that why more neutrons than the other. That is because you have this inverse beta decay. So you have a proton and the electron, they produce a neutron and a neutrino. So you are enriching the whole system by gas. Now you ask that while I enrich, p square by 2m is your energy, square root of p, all that thing, and then you ultimately reach a situation where it is all relativistic. And when you do that relativistic, put in the formula, you get 1:1:8. That whole gas, even let's start with iron, push it, then ultimately the A will come out. They will again do this 2 thing, and you take it to up to relativistic energy. Yeah. Yeah. And also this reaction, see, this is the most important one, that you are not letting protons remain. Proton and electrons are being eaten up, right? Yeah. Okay. So now Let's move on. Now, what I have tried to do here is that I have tried to show you that suppose you, so all these particle fractions that were there, take some very basic idea of an equation of state of a neutron star and go from the surface where the density is roughly, I am saying 10 to the power 11, we will come to this a little later. And then as you go inside in the star, you see this is the number of neutron fraction. And almost all parts of the star, the neutron fraction dominates the other fractions, the other equations that I just told you. So, this is the reason why a neutron star is called a neutron star, because it is mostly neutrons, fine. So, you go till the end and then you have other particles like proton fraction is this is electron fraction, this is muon fraction, okay. This is the nuclear saturation density 10 to the power 14, and this is your muon appears. So, muon appears when the density is slightly higher and so on, okay. So, this is clear. So, as we go inside the star, we of course have different cases, but now let us do that exercise what Chandrasekhar did, that you put back all fermions which are neutrons now, assuming that the neutron star is just made of neutrons in the relativistic limit, and ask what is the maximum mass. You can also ask what is the then you get a mass which is 5.7 m-sun, okay, and your neutron star radius is roughly 10 kilometer, okay. So, this is a very way to say that we have an object which is majorly neutron just from basic physics, and they are of this shape. So, now having come to this result, this is again a very beautiful result by the way. Let us proceed a little bit, that how do we now go ahead and say whatever we are saying is actually working in nature. So, here is so I gave you a very simple picture, but of course things are not simple. There is Einstein field equation. So, your hydrostatic equilibrium which you need to calculate the equation of state, the density and radius relations, pressure, density and so on. You have to solve these equations, which is Tolman, Oppenheimer, Volkoff equation of state. This is corrected for general relativity. And when you do that, roughly you get a picture which is like this. This is the interior of the star, and this is the surface, and your density is roughly same 10 to the power 14, 10 to the power 50. Right in the center it goes up to 10 to the power 15, and right at the edges drops very much. So, I took this front part and I zoomed it out to give some examples of the currently status of various experiments run, which are trying to probe at least this region of the neutron star, which is this fib, which it tries to tell out that when the neutron are dripping out. So, that is one EA. Then there is this one which is trying to find out this neutron skin, that means how much the neutron engulfs the EA, so that the interactions are much better understood. Then there is this heavy ion collision, this part. So, they probe something like 10 to the power 11 or something. So, these are the kind of experiments one is trying to do. They are also hopefully at some point get to this quark gluon plasma and so on. But all this that we are saying is a theoretical study till now, and one is trying to probe these things. But astronomically, there is a way to do this, because we just said that there is a mass and radius that we expect from this object. Okay? So, but the little confusion is that in reality it is not just a full neutron, right? There are other exotic objects. So, people have worked on this, particularly Mongevi has been very much involved in this kind of activity, trying to figure out the equation of state, putting all kinds, solving these equations, and figured out that there are two generic equation of states which give you the eventual results for a mass and radius. One are the steep ones where the radius is roughly very narrow range, but the mass ranges from something like 2.5 to this, and the other one is slightly soft, where the mass range is slightly, radius range is slightly higher, but the mass range is fixed. Okay. Soft and because if you had full neutrons, then it will be very stiff, right? Now you make a little bit of it will go soft. Okay, that's the idea of soft and stiff. Yeah. The bottom plot is just focusing this, zooming on this front part, saying that these are going to laboratory regimes now, and laboratory is able to probe these regions.
Okay.
See, we say the neutron is coming out. That's one theoretical experiment. Now you can do it in the laboratory. You can say what is the interaction between two neutrons. You can find the skin of the neutron and things like that. So one is trying to figure out that, you know, where they ride in the A, because there are implications for that in the R process, rapid process and so on and things like that.
So the top curve is drawn for a particular choice of central density, is it?
Yeah. No, so this has been solved, this hydrostatic equilibriums,
Yes.
which are here, and then you recover that as you solve that, because you have to put some interactions here. You have
So,
to
but
put some,
what is the input here? Is it the radius or the central density, or you assume you should be able to draw various curves for different central density? or something?
so all these range of things
Yeah.
will do a slightly different thing. I've just taken one approximation.
What is being changed here for the?
So here the thing has been changed, those interactions that I told you, what is the composition of neutrons.
No, but I should be able to change the central density also, no?
Yeah, I can change. I can
Okay.
change the central density by, let's say, an order of magnitude.
And then I'll get
Then
another
I'll get
curve.
another curve.
So
which
this one
might-
is for a particular choice.
This is for a particular
Ah, okay, that's what
demonstration,
I- yeah.
not the unit. If I put all of them, they will fill up this place.
So for a given equation of state, there is
That is
only
it.
a certain
There is a
range
certain-
of central
yeah.
densities where it is
Yeah.
stable.
Yes. Now
otherwise
another
it will become
equation of
unst-
state might have this one and look like this.
Yeah,
Another one might look like this.
right.
Those range of things are included in this.
Ah, okay. But if I take some very different thing, that might not be stable. If I take a very large central density or something.
No, that might not be stable.
Okay,
I mean, because you have to eventually also respect the other thing that it might go to a black hole,
true.
right? So if the mass is too high, then it will go to a black hole. Fine. You had a question? Yeah.
Change the internal dynamics of these neutrons and protons?
It does, and that one of the aspect I'll cover.
Okay.
Okay? Yeah. It does. You are correct. If it is too low, if it is too low, it won't be a no. So neutron star also, see, I have to allow that neutron drift, so I have to go past the white dwarf. Okay. So now,
Sorry, is that the blue line there? You know, if it is above the blue dashed blue line, then it is a neutron star.
no, the blue line is this neutron drip line. So this line tells you that below this, all the neutron stars coming out. Above this density is what I plotted here. Okay, I just expanded here this one. Okay, and this the top one is when the at some density you see the muons will start coming in, like I said. Then on the top, the green one is the saturation density. That is your 10 to the power 14 of a nucleus. Okay, fine. So now, so all this that we said, of course, again, neutron star does not form by putting matter. You have to, you know, there is an evolution of a star, and the star exhausts its fuel, and it undergoes through there. And you see that ultimately, when the star forms a supernova, you know, the Crab Nebula, the very well-known supernova, where there is a neutron star sitting right in the center. What happens exactly is that, you know, the material goes up, and suddenly there is a collapse of the material into, and it halts when it becomes a neutron supported star. Okay. Now in this process, there is a lot of things going on. One of the things that is going on is that the temperatures go very high, so there is something called a photo disintegration. Iron, as you know, is the binding energy per nucleon very high, so that's a stable electron. So these kind of equations where a photon, this photo disintegration hits, you get alpha particles and neutrons. Then there is a neutron capture, and you get a lot of neutrinos. One of the ways to get neutrinos. Okay. And the supernova explosion, of course, ejects outer material, the collapse and get all. And this is an example where you see all this was predicted by Bardia and Zwick in 1934, and it was observed in in much later, when the Crab Nebula was outed, not particularly in a system which is called supernova 1987A. Okay, and it is an event that we should be really proud about, because this is our colleagues here who one of the pioneers papers came from Indian Institute of Mathematical Science, okay, where you can see in the audience two very distinguished people, Indumati and I don't know where is Haridas now? Mysore, yeah. Yeah, this is definitely a seminal paper from this institute. Mm-hmm. Okay. Yeah.
From strings to, I will, yeah.
Okay, so here is the event. So there was an observation of a supernova which was observed in the Large Magellanic Cloud in February 23, 1967, and there were, like I said, that the event of core collapse predicts a lot of neutrino, but not only this equation, there are other equations that also lead to the formation of neutrino. And some neutrinos were detected by this Kamiokande, IMB Baskin, these neutrino detectors, roughly 24 neutrinos over 13 seconds. Okay. Now this number was the real, I mean, these people, why it is so wonderful a job is because you have to somehow get these numbers correct. Having that event and your detector, you have to say that thus 24 neutrinos is roughly what we expect, not like 100 or not like 2. That number is very important. Okay, and that's why this paper was definitely a very, very leading paper. I think there were a couple of others also during that time, but I thought that this is the one which now see, this confirmed theoretical prediction is not just that event, but it is really determining the production of these neutrinos to that precision. And there's a large number of processes by which these neutrinos can happen, and I am sure that there will be more talks about this thing. I will not go into this, but this is the real confirmation that indeed such a thing happens in nature. Okay, that something, when goes supernova, collapses, you get neutrino and you are forming something called a neutron star. Fine. So having known now that these things happens in nature, that's a neutron star, let's move on. That how do we actually see neutron stars? What's the manifestation of these objects? Okay, and currently there are a large number of ways neutron stars are manifested. The first pulsar was found, you know that they are found as pulsars. I'll shortly just say what is a pulsar, but that was in 1967, and this got associated with neutron star and a tick for a Nobel Prize, although there are many issues in this Nobel Prize, but let's not get into that. The range of things that one now is able to associate with pulsars or neutron stars are given here. So just wanted to give you the exhaustive list. But by and large, neutron star can be categorized in 3 domains by which we can do astrophysics and science. First domain is that they are seen as pulsars. So they are seen as ticks of pulses, regular ticks of pulses, very, very precise. They are like precise up to atomic clocks, okay? And they are seen in the radio frequency range. Not only radio today, they are also seen in the gamma rays, they are also seen in the X-rays. And the model one has in mind is that there is a star, neutron star in the middle, and there are strong magnetic fields. They go around, and then when an observer sees this, they see these ticks, okay? And one of the leading astrophysics question is that how do they manage to produce these things? I'll briefly come to that much later, but this is one rendition, that one way of it manifests itself, okay? The other way it manifests itself is that as neutron stars sometimes, they are born very hot. They are born with temperatures of 10 to the power 6 or 10 to the power 5 Kelvin, and you just barely see the star, as if you are seeing a black body. So this is just a black body curve with frequency, and is the second best black body probably in the year after the CMB. Okay, so you have such a nice, you can really find the temperature very accurately. And the other way you see is that it can be a binary, that it is sucking matter from the nearby star, and then these go and fall into the star, and then they produce bursts of emission. So all these various ways you can roughly study neutron stars. There are other ways like gravitational ways and etc., but this is majorly the kind of signatures. This one, yeah. Middle one is in X-ray. This is X-ray, this KeV, and these are 10 to the power 5, 10 to the power 6, that kind of temperatures. Okay, fine. So now the next thing is that our task was, when we started, that we got a rough estimate for the mass and radius, and we want to now answer this question observationally. How do we find the mass and radius? Okay. Now what happens is that, as I said, there are a lot of stars in binaries, pulsars in binaries, and some of the peculiar, from the very exotic ones are 2 neutron star, they go in one binary. Okay. But when you have binary parameters, even for neutron star with very point masses, you of course cannot find all the parameters, solve all the parameters of a binary, because there is an inclination angle which you don't know. And then you also solve the mass, which is a combination of the mass of the ratio. So you can not find the individual masses. So what do you do? So you appeal to something in general relativity where the binary, because it is a heavy point object, is also doing a space-time wobbling, and because of that you get a large number of effects, and these are called these post-Newtonian effects, which gives you further constraint to the solution of the binary parameters, particularly the mass. And you using pulsar timing, that this constant ticks, you can actually solve for many of them. And this has been done very, very accurately for several systems. One of them is really our colleague Kramer, Michael Kramer, he has been very much involved in this activity from the very beginning. And they found that this zone, that with these various parameters, they are given in different curves, but they kind of intersect in one place and they give you very accurate masses. So this is that zone where that mass for 2 systems can be got. All these parameters, they go and combine them. So now you can get a mass of the year, which is roughly 1.3 for the 2 masses. Okay, so very close to this 1.4 solar mass system. Okay, but of course neutron stars can go beyond that mass. Okay, and people now have applied that thing to a large range of systems, where these are various methods by which I have not gone to all the methods, but this is the mass range. So neutron star masses has been measured for different cases. You see, this is the 1.3, that double neutron star that one had. Roughly this place, and the maximum mass that has been found till now is 2, but there is a recent detection that I just heard is 2.4 solar mass. So we are very much in the ballpark of, that naive calculation gave you 5 point something. But of course we cannot get 5 point this, because equation of state is not just neutrons. Okay, so this also gives you sufficient confidence that we have some kind of an equation of state that belongs to a large number of effects that we just said. Okay, so now moving on. Next is we have the mass. I showed you a distribution for mass, but we need the radius. Now the radius calculation basically comes from that black body that you showed. A lot of systems have the black body. So you take the temperature of that system, you can associate it with a black body T to the power 4 kind of relation. But neutron stars are gravitationally, it can bend photons. So you have to do a correction for that and eventually get some radius. And now here, for example, there is a large number of systems where you have determined both mass and radius. So you get this kind of 8 to 12, some range of radius in the various systems. And this is also in that ballpark, 10 to 8. So the problem of what are mass and radius of neutron stars have been sorted out. Let us put a few of them back into this business. So those kind of methods, very recently some good well measured gives you this mass and radius, they kind of prefer the stiff, that means more of neutrons here. Except that recently there was another thing that happened that you know is the this object which is sorry. So this is once again that same method by finding the mass and radius through black body, and they put these constraints here. But the one which I was trying to tell you is this one, the gravitational wave that is coming from this object, where two neutron star came together and ejected material and gravitational wave. Now you can use some of those parameters measured during that system to find the mass and radius. One is the chirp mass, one is the tidal deformity, and they give you this constraint, this one that you see here. So it somehow prefers something which is mighty softer. So the question whether it's really soft or depends on the model, etc. But bottom line is that we are not very far away from that general. Okay, maybe different neutron star have different equation of states. We don't know. Okay.
Determine the temperature of a neutron star because you see only pulses.
No. Probably missed this. In some neutron star, you do not see pulses. You see simply a hot black body temperature.
Oh, you can see that. Okay.
Yeah, we see in the X-ray, it is the second best black body in the universe. There are 7 magnificent, they are called magnificent 7, and they absolutely give you this pure black body kind of.
But the temperature is so high, it's in the X-ray range and so on.
Yeah, 10 to the power 5, 10 to the power 6.
Thank you.
So in that mass radius plot,
Yeah.
the uncertainty in the mass is shown as the height of that.
This one, yeah. This 2, yeah. And the radius, we are still, people are still finding individual objects. There are not so many compared to mass. But whatever they are believed, these are some best measurements that have been given. They seem to at least lie in this range.
No, but if I take the blue line, the uncertainty in the mass is the height of that line, or what? Or is that not?
The uncertainty, I think it is here, very accurate. But you see, these are all a little model dependent, okay? Because the tidal model, how much these are dependent on those, okay, not this one, but sorry, this one. So this depends on your love number, which is basically telling you how yeah.
So the uncertainty in the mass is not shown there in that plot?
Uncertainty in the mass, I would say, is not really shown in the sense of here, because the radius was something which was more accurately determined. Yeah.
Good morning, Professor. I was just asking, during this neutron star, there are 2 phases, right? The pulsar and the hot neutron star. Can we, during the process of formation of this neutron star, can we predict which one would happen, the pulsar or that hot black body thing?
Yeah. So when you say a pulsar and a neutron star, it can be possible that the pulsar is emitting like a beam.
Yeah.
So maybe the beam is not looking at, maybe it's already there, but you are only seeing the surface of it, the other side. It's like a beam, right? So if it is not towards you, then only you will see the surface which is towards you. Okay? It might be that this has failed. So there is no correspondence as such one can associate when it happens. Okay? But suppose you see a pulse, then you can look for during that pulse whether this object has a hot phase also. And there are several objects where you have found that also. Okay. But there is no prediction that you can make because they happen in a slightly different manner. They are different physical scenarios. Okay. I will come to it a little later maybe.
Thank you.
I am going very slow maybe. Okay. Fine. Okay. So now having settled the issue of mass and radius, we then have to take some confidence in this cartoon picture that there is probably there is a neutron star which has different material. It's not 5.7, so it's not all neutrons. So there is some other kind of materials which are existing as we go below. Not only that, there is a crust. There is also a inner region which is given by the this ion lattice soaked with a superfluid. then there is an outside core, and partly in answering your question that inside the neutron star it is not just the normal matter, it undergoes through superconductor and superfluidity as one goes down, and more towards the center it is reasonably unknown, but they are mostly quark, gluon and things like that. Okay. So now there is another experiment, there is another aspect that was found that one can understand from neutron stars is the production of heavy elements, okay, like any elements which is more than iron and things like that in the universe. We have a lot of heavy elements, and where do they come from? So it so happens that neutron star is really a factory for such elements. It has been proposed for a long time, where something like a neutron capture can happen, and this is this valley of stability. So you have an atom, then you absorb a neutron, you increase your A plus 1, and then beta decay, it again goes back. So this is how a neutron rich thing will happen, except that if you can make this rapid process very fast, a succession of neutrons can go before this happens, then if you start with a material which is below this element, you can quickly pass that and go there, and then you can slowly decay it back and crawl back to the center where you have gold, etc. and so on. Okay? These are stable elements. This is how you would like to do this, and this is exactly what was observed in this gravitational wave scenario where two neutron stars merged, the one which I just said a while ago. Okay? You also observed that there was some kind of a huge kilonova, what is it called, a kilonova, that means some kind of a explosion, and the thermal energy of that explosion went through the atmosphere, and they detected this dip. Okay. And this dip corresponds to, after a very reasonable analysis, to something called strontium, okay, which is it's 88 strontium, which is apparently a light stable isotope, okay, which was formed in this process through that R process. Okay, so this was the first detection of a lighter isotope than in this process, and so I did not know about strontium before this. So only after this I know that there's something like strontium exists. So it was interesting. So anyway, you see that this is also now detected. So it is again a factory of neutron and how these processes are gone. So we have gone a long way from simply mass radius. There's also this. So next, let's move on to. So I showed you a picture which showed that there is there's a crust, and then as you go down, there is superfluid. And in the superfluid story, of course, you know that superfluids were discovered in 1911 and so on. But even before neutron stars were discovered, in 1958, this Migdal already predicted that there is some kind of a Cooper pairing happening in neutron star, leading to superfluidity. Okay, and then you see a large number of work. Soon after the discovery, there was some observation glitches which was associated to neutron star, and there is a large body of work till now. So I'll focus a little bit on this. So what does it mean? So now. So neutron superfluidity arises due to Cooper pairing, just like superfluidity in anything, by the nuclear force, and there are different channels. They depend on the density and temperature, roughly speaking. So if you increase the density and if you reduce the temperature, at some point in neutron star everything is cold matter because the density is very high, although the temperatures are very high, and so you can basically, as you go from the crust, at some point just below the crust there is a point where the conditions are such that you can basically get a superfluid. This line tells you at particular density and these temperatures are the pairing temperature. That means below that you will get superfluid. Okay. So even if you go much inner, you will get proton superconductor. Then much below you will get another kind of pairing, not just the 1s0, that means not just one kind of pairing, there are different kinds of pairing, p orbital, s orbital and so on. And so this is how you get this pairing depending on the temperature and yield. So this also, as you know, this is somewhat phenomenological, but it is model dependent, but one roughly knows that there is superconducting and superfluids inside a neutron star. Okay. So now let us let us not get into the details of this, but just see how we can detect this. Okay. So, the first thing that neutron star superfluidity was detected was of course the glitch one, which will come a bit later. But there was another interesting event that happened in this supernova, which is inside the supernova there is one of these objects which is a neutron star. Now you ask that where is the beam? Okay. Now in this is a supernova and there is actually a central object like this, but it is not pulsating, but it is hot. You can see it like a hot X-ray. Okay. So you can measure the temperature. And suddenly what happens after this supernova is not something that we have any historical records that one has seen, and it is given the size of this supernova, you can calculate something like 330 years or something. And what one can do with this object in the middle is that you can go on monitoring its temperature. Now suddenly what happens in the last decade or so, this temperature, it suddenly fell much faster than the other times. Okay. Now what does it mean? That neutron star was formed with a temperature in the center and slowly it radiates, and then it slowly goes down to that temperature where superfluidity can set in. As superfluidity set in, when you have neutron neutron pairing, you also release neutrino. And in that process, you can actually cool down the star very fast. And these lines that you see are actually models of that cooling, very, very accurate models. Okay. And this means that the star suddenly after cooling went down to a superfluid stage. Okay. This was the evidence for the superfluid. Just below the crust, you have some superfluid which was formed due to the cooling of the star. Okay. Because the temperature, just follow my cursor, the temperature was going like this, steady, then suddenly the temperature fell like this for a decade or so. Now this fall of temperature needs some release of some energy.
Sure.
That release of energy is coincides with the fact that the temperature inside the star falls forms superfluid, because that number of cooling, the time scale of that cooling coincides with that time scale of the fall.
No, but that's theoretical, right? At a given temperature that it should be superfluid is the theory. We don't know directly, or do we know directly from observing that it is
no,
in
we
a
cannot
superfluid?
see the superfluid. We are indirectly, yeah, of course we can see. Yeah. But there is no counter theory to that also at the moment. Yeah.
Earthquakes, so they're all observational consequences
Of superfluidity, yeah. Yeah. And that is what I will come to next.
Can I just interrupt? This neutron pairing with neutrino emission. Can you say a little more about it? What is that PBF, first of all?
Yeah, pair formation, pair breaking and formation. So when two neutron comes close to each other, they form a neutron-neutron pair.
Okay.
But they'll also release some energy in the form of neutrinos.
Oh, so they're just radiating neutrons.
Yeah, weak
It's not neutron-proton conversion.
No, this
Okay.
is weak interaction. No?
Oh, these are the cooling neutrinos.
Yeah, the cooling neutrino, and this is
okay,
very
okay.
efficient.
I see, I see.
And you almost never get, to answer your question, this process is very efficient to actually
Cool,
cool down
yeah.
the star.
So is there sorry to interrupt again, so is there an estimate of the number of neutrinos that would have been emitted? Of course, very low energy, but still, I mean.
Yeah, it is not detectable by the
Okay,
way, but it is, there was an estimate, I'm sorry, I don't
Okay,
recall
okay,
it, but there is an estimate.
I'll look it up, thank you.
The analog in nuclear physics is that nuclei are superfluids.
Yeah.
Okay, so is there a rough measure of the moment of inertia? Because if these are rotating.
Yeah, so that is what I will
so
come
that,
to.
that will also tell you. The moment
Yeah,
of
absolutely.
inertia of a rotating nucleus is of the order of half or so,
Yeah.
when it is in a paired state.
Yeah.
As the angular momentum increases, the pairing correlations decrease.
That's
and then you tend to go towards the rigid body moment of
Yeah,
inertia.
you're absolutely correct, and that is another part of the story of this thing. So which comes in the form, yeah. Yeah. Yeah, I mean, I think that they are emitting definitely a large number of things, but of course our detection ability, but the main cooling mechanism, the neutrino overwhelm everything. Yeah, yeah, sure.
Or are we? Okay. This business of the neutron core was, I think, to my mind, the first instance of saying something like that was Bethe in 1936. So he said that, if the mass is larger than that of a white dwarf, then it will collapse and you will get a neutron core. Because
No, I think it was Bade and Zwicky.
Did they talk about neutron stars?
Yeah, they were the pioneers in trying
because
to.
I found this in a footnote in the Bethe paper. He says, if it is larger than that, then the core would be a neutron core.
Yeah.
I thought that he was the first, but okay, maybe you are
Okay, so now okay, so we just established observation which tells you that there is superfluid in neutron stars associated with the cooling. Now there is another phenomena which is very interesting. So this is, for example, a pulsar which is called the Vela pulsar. This pulsar, it is a pulsar which have ticks that means they rotate every 89 millisecond. Okay, and now this when a pulsar rotates, okay, a pulsar has a large magnetic field outside. Okay, so because they rotate, they are like an unipolar inductor. So they also radiate away its energy, and as they slow down. So if the pulsar is actually, in fact, you can calculate this slowdown, and for 1 day, this pulsar would slow down by 10 microseconds. Okay, suppose I take the whole day, this 89 millisecond will change by 10 microseconds. Okay, and so the pulsar is slowly lengthening its period, and that's what you see here. Here's a plot, and again, Radhakrishnan and like Manjari mentioned that one of the pioneers, Radhakrishnan from Raman Research Institute, who worked a lot on pulsar and set up a pulsar group there. He was involved in this work where you see initially there is a large increase of period of the pulsar, that means the ticks are going longer and longer. Then suddenly there is a jump, very sharp jump, and then it stops that jump and it continues, and eventually it will again go and connect to that. Okay. So this is the phenomenon that this is called a glitch. Okay, so a pulsar is rotating, then suddenly it will jump. Jump in means that it will lower its ticks. Okay, and then it will again go up. Okay, and this was once again connected to the only known theory for this is actually the superfluid and vortexes that you are talking about. So let's see about that. Okay, so what is the history of vortices? Now maybe I don't need to go into detail, but just to mention that there is a large history of the superfluidity and vortices, and the idea of quantum vortices were borrowed to explain this phenomena. So what happens is that, so if the vortices arise because of the following, that if you take a superfluid and rotate the vessel, then the wave function is no longer continuous. There is some kind of you have to have obey the boundary condition, and to obey the boundary condition, the way to do that is you create a lot of vortices in the direction of the rotation. Okay, in the fluid. So if you have superfluids inside a neutron star, you do that. So there is a large number of such vortices will be created. And these vortices, if you have a crust, that means the inner side of your vessel, if it has some undulations and so on, then they can actually pin to those vortices. So these things would, like, if you take one of these, they would pin to the surface. And as I said, the star with time, it basically slows down because of that externally. But the superfluid does not slow down in the similar speed. So what happens, you have a rubber band effect. Something outside is rotating, but inside slowing down, but inside it is faster. Slowly that stretches, and some point this so-called Magnus force, which is like how it comes out, it releases itself, and then you jerk the star. Okay, and that's the glitch that we observe. And this is the only known example that we, only known way we know to explain this phenomenon. A sudden rotation of a 1.4 solar mass object in such a short time and again coming back. Now, you see in the laboratory, you can create these are the number of vortices you can create in the laboratory. But in that fluid, you can create 10 to the power 18. So, when you jerk this thing, you have a large number of vortices that is participating in this activity, and that's why this is probably not seen in the laboratory. We do see this in neutron star, and coming to this effect of moment, yeah. There are multiple estimates, okay, and right now they are actually doing this in a computer, because 10 to the power 18 is a big number. So, to get there are this computational thing, I hear that they are still not at the level where they can exactly reproduce the scales, but there are phenomenological estimates for them, and they roughly go to the order of the star itself. Sometimes at least that's what I heard, but I'm sorry, I'm not an expert in this area. Yeah. So, yeah. So the point is that so this moment of inertia thing that is there's a way to estimate how much the superfluid can dump its moment of inertia onto the surface. But we also need to remember that the superfluid is also not pure neutron. There are other effects. So there is something called entrainment, that is dragging. And so if you put some kind of estimate of that, again it's a theoretical estimate, then you find that the amount of moment of inertia that is transferred from the superfluid to the star to do this thing is not sufficient. So you need to engage not just the crust, but maybe the superfluid of the core also. So, but these are really theoretical directions, but they are interesting theoretical directions. But nonetheless, the basic effect, the glitch happens from the effect of vortices, is something that cannot be refuted, I think. You have to find something else to do that, okay? Particularly the time scale over which it happens, and also the time scale it takes to recover. So once you do this, it breaks, then these vortices slowly creep back, again they form. And all this time scale, they really match with a simple idea of vortex. So this is another thing that as we went to the interior of the neutron star, we also found that there is indeed superfluid. Okay, fine, yeah. Oh, there are many glitches. Yeah, and the typical time scale of glitches is, I think, roughly 2 years or so. So where is it? Yeah. Oh. So 600 glitches have been observed in 250 pulsars. The size of sometimes the time scale over which it grows up and down and so on, they change. So there are the coax also, yeah. So various kind of such things, and this is all related to all that. Fine. So now, having touched upon the interior of the star, it's time to go beyond. Okay. And we definitely have made this claim that neutron star has high magnetic field, but then all that I have said till now, I have not included magnetic field at all. And you might wonder why is the reason, why magnetic field is not important for all these interior physics. The reason is because that if you take the magnetic, even with these high magnetic fields, 10 to the power 12 or 10 to the power 13, the matter density as well as the ratio of the magnetic field and the matter, it's 10 to the power minus 10. So absolutely, if you go interior of the star, it doesn't matter at all, except right at the surface, and we'll come to that a little. So now, I told you that there is a spin down of the pulsar. That means if you have a unipolar inductor, that a magnet which is rotating in space, this magnet will slow down. And it will slow down simply because there is a magnetic field and it is changing. There is a del B del T, that means the magnetic field is changing with time. So because there is a del B del T, there is a electromagnetic field that is being radiated out. It's of course a global electromagnetic field. It's not like a pulse or anything, but the result is that it is taking its energy from this rotation, right? So now, if it happens, and if I can measure that, that means the steps of its period and how it slow down, you can actually measure the period and the derivative of the period and get an estimate for the magnetic field. And this is the group of pulsars all along in the neutron star population. Today we have more than thousands of different kinds of manifestation, and you see the magnetic field is found to be roughly of the order of majority of the group is 10 to the power 12 Gauss. These are one kind of objects which are called millisecond pulsar. I will not have time to go into this, but this is also another major contribution that comes from Raman Research Institute, Srinivasan and Radhakrishnan and Dipankar Bhattacharya. They gave an explanation how these magnetic fields are lower. They are being in binary systems, recycled objects. But we also have many objects which are roughly, 10 to the power 14, 10 to the power, and this is the critical quantum magnetic field line, okay, 10 to the power 15 Gauss. And these are multiple ways to find. One is, of course, that way. Then you can also have cyclotron features. That means the thermal emission that I said that's going through an atmosphere, and you can get a cyclotron line. In fact, let me show you that. So here is a nice thing from our telescope. There's an Indian telescope, AstroSat, where you see that one of these thermal emission from the neutron star going through the atmosphere, and they are getting absorbed through cyclotron lines. And here you get a spectra in the X-ray, and this spectra, if you take out the background, you see a line here. This is the electron cyclotron line, which lies in the X-ray regime, and you can find a magnetic field using that. Okay, so you find this 10 to the power 12. So this is also direct measurement. It's not just that slow down, right? It's directly at the surface you measure the magnetic field. There are many such examples today. There are other ways. I told you magnetic field. Once again, I don't have time to go into this. But you get those estimates very well. Sometimes you get estimates of 10 to the power 15 Gauss and so on. And what is the outcome of that? That means that the fact that you have very strong magnetic field at the surface. One of the outcome there is that the surface is, the magnetic field is so strong. I told you the magnetic field inside doesn't matter, but right at the surface where the density is going down, you actually cannot keep the electrons in these s orbitals anymore. Because of the magnetic field, they will be in the lowest Landau level. Their orbitals will now become, elongated along the magnetic field. Nearby orbitals will overlap. They will form some kind of a covalent bond, and you will have a very, very strong, crust where everything is, combined, and the cohesive energy of any atom there will increase. For example, here is an example. If you calculate these, binding energy per cell and the cohesive energy for the atom energy, with this ln b square, they come very naturally in this theory, density functional theories. Then you basically get a dependence on magnetic field, and you see that how the electron binding energy. The electron binding energy here is roughly, few eV in the Earth, but there it goes to 100 keV in a neutron star. So just pull up is not easy, even a hydrogen atom. Okay, you need really strong fields, strong electric fields, and so on. So this definitely affects the stars. And now let's go back to that black body. Yeah.
Why is it that there is no magnetic field inside the?
No, there is magnetic field. It is not affecting the structure.
Oh.
Because the density is so high, they are so close that your Coulomb levels or nuclear forces, etc., they are overpowering the here, but not at the surface. Surface is exactly the opposite. Okay. Fine. So now wanted to come back to this in the fact that we said that we see very pure black bodies in neutron star. Actually, this could be the reason because of that very condensed surface. Because if you don't have such a condensed surface, then it's a black body is a very special situation, right? I mean, you have everything that is coming, all for all those textbook kind of thing has to happen. Okay, and that can happen from a shiny ball, for example, a red ball, like you have imagine a black body like a red ball radiating towards you, and that is exactly what the EA offers. And so these are featureless black body. There's nothing. It's just a black body. Okay. So that's one motivation to see do that. There are other motivations which we can talk about separately. But now let's go to another effect, which is called vacuum birefringence. Okay. So we are now outside the neutron star, and the neutron star has magnetic fields which are 10 to the power 12, 13, 14 cos, which is very high, and there is a large number of effects that can happen. So this is the magnetic field here, and there is a large number of effects that can happen. One is vacuum birefringent, okay, which is if you have magnetic field in a vacuum, the vacuum acts as a catalyst, some kind of a catalyst, and your electron-positron pairs appear. Although, so you get when light goes through that, it will feel it will not feel like a normal layer, and most of you know this effect. There is another effect which is not necessarily seen in the laboratory, which is that when a high energy photon more than this 1 MeV photon, that means greater than the rest mass, 2 times the rest mass, then you can produce an electron-positron pair. And there is also another effect which is gamma-gamma splitting in the prism, where a photon splits into 2 gammas. Yeah. Not so strong. Schwinger effect, you mean? Schwinger is laboratory is better. Yeah, it is there.
That is the one that is creating.
Yes. Okay. So now you see, let us now see that whether we can detect these effects. Okay. And one other thing is that, as I said many times, thermal X-ray, that means the star is emitting some X-ray. Now let us say that there is a star, and then of course that matter that I told you, that might actually create an atmosphere, small atmosphere, because of the nature of that material just at the surface. And then ahead of it there is, let's say, just vacuum. Okay. Now if a black body radiation goes through the atmosphere, then what happens is that you can basically, this atmosphere is going through high magnetic field. So it will be birefringent. That means your black body has radiation which is k vectors, or it's random k vectors, the direction, random direction. But when it goes through vacuum which is highly magnetized, goes through atmosphere which is highly magnetized, you only allow certain modes to go. And the modes that you allow, you can calculate it very easily, are the modes which are perpendicular and parallel to the KB planes. So if you have a direction of K and external magnetic field B, you have a mode which is perpendicular to this, or they are in the plane. Okay, these are the extraordinary and ordinary modes. So now when the thermal X-ray goes to this, you have a X mode and these O modes which are going. Now the magnetic field is so strong that the particles cannot go out of the field. They are all in the last Landau level. So the mode which is in the plane, they get absorbed, and the X mode can simply go out. Okay. So X mode, as I said, is the magnetic field which is perpendicular to this. So if I measure some polarization from the neutron star, some radiation, I should get something which is, some direction of the polarization. Okay. Of course, this direction, an interesting thing happens that as the thing is going, there is also refractive index by the vacuum, because vacuum also has now some kind of a plasma. And there is a resonance happens such that the X mode goes to the O mode due to the vacuum birefringence. Okay. It's a very interesting phenomena. It's something thought. In fact, not only interesting, this is now observed. So what I wanted to say is the following, that you started with this X mode. So this is some, I mean, forget all this thing because I don't have time to get into that. But you start the radiation of a thermal radiation and you say that O mode has basically vanished. So this is the vacuum representative of the plasma, the atmosphere, the behavior of the atmosphere, how the polarization propagates. And then at a certain density, as the thing goes away, there is a resonance, and this X mode gets translated to this O mode, and then it continues to go. Okay. So as a result, what happens? This is an indication of that angle. So let's say this is the X mode, of the energy of a photon, you suddenly see the energy of the photon has turned by 90 degree. I really don't have time to explain this, but think of it like this, that there was an X mode that was going out like this, and then because of vacuum birefringence, there is a resonance that happens and it turns it into the O mode. Okay? And this is actually observed. Now, there are a lot of, this is very, very recent findings. These are, that is, you're finding vacuum birefringence in the claims of vacuum, but there are other issues to be sorted out. The very neat environment that I have said, that you have something kind of atmosphere and vacuum outside, that might not be true. There might be some plasma. But nonetheless, this is a very good direction to start, and many telescopes, particularly this imaging X-ray polarimeter that is currently available and so on in the recent futures, will participate in finding this. Okay. Next, so I have many more things, but how much? 5 minutes? Okay. Okay, so I'll just go through this. Okay, so a vacuum birefringence is supposed to happen. It's not observed in the laboratory, but here is a system where we can basically try and probe, and I of course can discuss with you how this is done. I've hurried through it, but main idea is that you use polarization, the eigenmodes of the polarization in strong magnetic fields, which has some features which allow you to detect them. Okay. Next is, the neutron star, of course, so it's a star with large magnetic fields, and it's not just atmosphere and vacuum birefringence. You also have this magnetic pair creation and photon splitting. That means in a strong magnetic field, a high energy photon in the ambient region will create pairs. They will cascade and produce further pairs. So here is, for example, you see the probability of, as a function of magnetic field. This is how photon splitting happens, the probability, and this is how your pair creation happens for a 100 MeV photon. Okay. So neutron star lies in this region. You see that this is a dominant feature in terms of the relative probability of here. So we expect a large number of particles to be created around the neutron star by this process of magnetic pair creation. Okay. And it is electron positron plasma. After all, we need plasma to create the radiation, right? So this is the source of that plasma. Now, if that source happens, once again, I will not get time to get into this, but let me just mention this. This source, again, in that plasma, this radio emission that we get from the plasma will follow this similar laws of eigenvectors. That means polarizations will be parallel and perpendicular. And this is another feature that we actually see in pulsars. It's a kind of work that I have been involved for a long time, where my aim was to really find out that whether we get this extraordinary and ordinary mode, which are 100% polarized signals from the neutron star. This can only happen when you have collisionless pair plasma in neutron star, and in fact these signatures, which I can explain to you independently, do offer this scenario that we see collisionless pair plasma produced by magnetic pair creation. So you have collisionless pair plasma in a stable uniform for long time existing, where the eigenmodes of the plasma are these extraordinary ordinary modes, and they are detected in the radio. Okay. So you confirm the presence of here, which is another interesting experimental area. Yeah. Okay. So finally, axion. Yeah. So this is another area which has become very popular these days. The idea is, of course, you all are more experts than me, but the main idea is that the axion can couple to the photon. So your Maxwell equations get modified. So there is a gradient of this field. So if there is a gradient available for this field, you will get an electric field. If there is a change of temporal change of this field, you will get a magnetic field. So you get some electromagnetic radiation. So that's the idea. And so neutron star, apparently the effect of this is of course very small, but neutron star, because of this magnetic field, this effect can be detectable. So there is a possibility that you pick up those neutron stars which have very atmosphere free, show this black body kind of thing. There not much plasma is around them. And then you try to figure out ways that these axions can affect the temporal behavior or the spectra or things like that to figure out the renditions by which we can detect axion. It's a very difficult stuff because we have many more external effects, but nonetheless this is an idea people would like to follow in the field of neutron star research. Finally, I will just mention to you that India has been very actively involved from the very beginning of pulsar discovery and so on in observing and trying to study neutron stars in the astrophysics. So we run, I come from this facility which runs these two instruments. This is the UTI radio telescope, this is GMRT. We do observation, and what Manjari, for example, is involved here is trying to use GMRT to study the gravitational wave detection, the background, by using pulsar timing arrays. This telescope has been very effective in producing a large number of pulsar results and other things. It was established before GMRT. Then we had this AstroSat. I showed you one result of AstroSat, although these instruments have not produced many, but whatever they have produced is also pioneering. So we currently have something called an X-ray polarimeter, XPOSat. We are still awaiting some good results from this, but clearly, we have the potential to do a lot of good neutron star research. And as I said, that your involvement in this kind of study is, of course, most welcome, and please free to ask me if you need some support or help. Thank you.
Thank you, Deepanjana, for such an exotic talk. And probably you forgot to mention that XPOSat is also RRI, designed by
Yes,
RRI.
yes,
So RRI is still one of the pulsar capital in the world, not like Radhakrishnan's day. So we have time for one or two quick questions, and then we have coffee because there are many other exotic talks lined up. Okay, good. Okay, yeah.
XPOSat. When was it launched, and what are the main goals of this XPOSat?
It was to do polarization of few objects. It was not a very sensitive one, but a trial mission to see whether one can do polarimetry in star. They launched, I think, 23.
Okay.
Till now, I have not seen.
So, how many experiments are there on that?
Two. One is a spectrometer and one is a polarimeter.
X-ray spectrometer.
Yeah. So two of them, and they had initial first lights, but not beyond that. I have not seen much.
Regarding the section on axions, so what is the main goal here? There is a plan to constrain the axion masses from the neutron star observations?
Yeah. I mean, this conversion, photon conversion, if you know the conversion, then you can go back to the electromagnetic theory and find the A field. So
mainly you see the magnetic field, how it changes, and from there
not magnetic field changes. So that is why it's a little difficult, because you are looking for an electromagnetic signature. See, you now remove the charge. If you have a charge and a current, you get electromagnetism. Now you say I have axion, I get electromagnetic wave. Now except that axion electromagnetic wave will be much weaker, and this much weaker, how to decouple all that from other emission mechanisms and things like that. Is there a way to do that? These are very, very difficult problems at the moment. And my belief, I don't even know how to attempt this problem at the moment. But this is a thought, at least. Okay, so but I thought that Madhavan mentioned this.
Yeah, I just want to recall our good friend Vikram Soni at this time and pay homage to him. He was a great guy. He was a good friend of Mad Science and many of us, and he was a faculty at University of Madras. So in his last period, a few years, he had ALS, but he was strongly working on this binary kilonova. So he had some equation of state which had neutron superfluid, neutron crystals, and then quarks soup. So he had some explanations. Unfortunately, he was fighting with the referee, and he had ALS, and he was a fighter till the end. Amazing guy. So I just want to
he is
recall.
very well,
And
he's a
he's also-
fighter, definitely.
Collaborator of Dipankar, your
Yes,
boss.
yes, you're correct.
So we talk about Stephen Hawking. So I call him Stephen whenever I met him. Delhi Stephen. Thank you very much.
Yeah. No, thank you for reminding me. I mean, he was an extraordinary colleague, and of course, he passed too early, and I would say, but extremely jovial and always at his.
Okay, so if there are no more emergency question, we can break out for coffee. And when should we come back? 11:20? Now 11. Okay, so let us come back from, at 11:20. Actually, I am trying to invite him for last 11 years, but I never succeeded.